Okay. Hi, everybody. I'm afraid today we're only doing a recorded um, uh, version of the class, and let's hope I don't screw up too much, and it works for you guys. Okay. So the first thing I want to do is go over the small signal model, just because I know it can be pretty confusing. So small signal signal model review. And I'm just going to say kind of the same thing I said in the last lecture, maybe in a little bit of a different way, or just reiterate what I said. But and again, I know it's a difficult concept. I don't think I really quite got it until I really started designing circuits for a living and seeing how useful it can be. But anyway, in the end, it's just another, this is just another simplifying model. Okay, simplifying, I'm not sure how to spell it, flying model of the diode. And the idea is this, that, the diode is the diode. It has this voltage versus current characteristic that we're used to seeing. So that doesn't change the small signal model. The idea behind the small signal model is that you basically operate the circuit around what's called a bias point. And there's a voltage bias point and a corresponding current bias point. Okay. And so you just operate it in a very small region around this bias point. Okay. If you have such a situation, so just have a small delta V around your bias point, then you're going to have a small delta I around your current bias point. And you basically, the cool thing, I guess, is the usefulness of this model is you run into this situation all the time. So anyway, if you can, you're sitting at this bias point at the central location, and your signal is just a small permutation, a small modulation, a small movement around this point, which with a corresponding small movement around your current. So if you zoom in all the way here, just for this point, okay, just as for this one point, you can assume that this range, which is, the range of your V, let me zoom out a little bit so I can write, V bias plus sort of minus your delta V, which in the current space, when you look at the current axis out here, it gives you I bias plus minus delta I. So just for this range, you can pretend like this current, this slope is linear, and that therefore you can model it as a resistance. So R sub D is V sub T over your I bias point. Okay, so that's the sum total of it. You've gone from, initially you had an exponential equation that describes its characteristics. Now we're saying, okay, you still have the exponential equation, okay, but if you just stay in this small area and just don't go too far this way, that way, don't go too far this way, that way, you can just pretend like this is a line. And this ends up, given that if you're guaranteed that you only have a small amount of change, then it's a very good approximation, and it makes your calculations very easy or much easier. Okay, and so let's see, what else do I want to say this? And what is a small delta V? So you're really comparing, because remember the equation is I sub the equation in this forward bias, this approximation already we approximated by VD over VT. Okay, this, if you're looking at this, then what you're really concerned about is the ratio between the change in voltage to V sub T. So basically you want to say that if V sub D is small compared to V sub T, okay, which is 26 millivolts at room temperature, then this makes for a pretty good model. Okay, and so you know how good it is. It's, you know, it's again, it's a model. It's a simplifying assumption that is simplifying your calculation. So it only goes so far, but it's really good. So let's just do an example and to compare or to see first of all how it works, and then compare it to what would happen if you didn't use this simplifying assumption, and how much more difficult your life could be for a similar calculation. Okay, so this is an example of from, let's do this example. It's example 3.18 in the book. And I'm just going to do the first half of it, but I'm going to do it in 2 flavors. Okay, so what it says is, assume you have a you have your diode, exaggerate this. Okay, so assume you have your diode, and assume that you are biased around a 1 milliamp mark. So that's where your diode is kind of centered around. And so this gives you a effect, you know, a corresponding V bias. It turns out, you know, once we have the I bias for this problem anyway, we don't even need to calculate V bias, because remember, R sub D is just a function of I bias. Okay, but anyway, we'll get around to that. So we're based on I bias, and the question is, how much would I bias change if V bias changed by, so if delta V was 1 millivolt, what's delta I? Okay, so let's do that first. So if I go here, is I bias is 1 milliamp. So just in this area, let me put it in some other color, purple maybe. Just in this area, just in the small area, I can assume that R sub D is V sub T over 1 milliamp. V sub T is 26 millivolts over 1 milliamp. So I can assume R sub D is 26 ohms. Okay. And if my delta V is 1 millivolt, then delta I is just equal to delta V over this effective R sub D. So I'll call that R sub D1. Okay, so 1 millivolt over 26 ohms. And this ends up being 38.4 microamps, which is your answer. Okay, so a pretty straightforward calculation. If I dared do 1 over 26 in my head, this certainly was easy enough to do in your head. And then, you know, you can easily get this 38.4 real quick. Okay, let me just do another example. I mean, this example, but with a different set of numbers, just to give you guys an illustration of what would happen if we now pick a different bias point. So, okay, so let me move this down. Give myself a little bit of room. Okay, so now let's say that we said, okay, what if we picked an I bias of 2 milliamps? So what if it was, our I bias was 2 milliamps? That would give us a different V bias. So this would be V bias 1. What would a 1 millivolt change do around an I bias of 2 milliamps? Okay, well, it's a small signal model, so we have to zoom in here and calculate what the resistance is here. Notice that the resistance here is going to be different than the resistance here. And it's only, so this resistance was only good for an approximation of this small sort of distance here. This new bias that we're calculating, this new resistance that we're calculating is only going to be good for this region here. The reason is this is an exponential curve and the slope is changing depending on where you're centered at. So if I do, what would happen for I bias, what would happen for I bias of 2 milliamps? Well, R sub D2, so I'm calling this R sub D1. R sub D2 would be V sub T over 2 milliamps, okay, which would be 26 millivolts over 2 milliamps, which would be 13 ohms. So my resistance, if I bias the diode up at 2 milliamps, my resistance goes down by a factor of 2, okay? And it kind of makes sense from the slope that the resistance here is going to be less than the resistance here because the slope is sharper than the slope here, just for this small area, okay? So if I do the same delta V around this point, okay, then delta I, so this is 1, delta I2 is going to be 1 millivolt, 1 millivolt over 13 ohms is what do we end up with? Let me see, if we bias it at 2 milliamp, a change in 1 millivolt now is going to give us 76 microamps of current change. So notice we increased our voltage to current gain essentially by operating the device further up the curve. And it makes sense because here, as you can just see from the curve, if you have a small change in voltage, it will give rise to a bigger change in current than you're down there. And operating down here would be even a smaller change. Okay, so that's the idea behind the small signal model. Now, let's say, so just to, again, I'm trying to illustrate the benefit of the small signal model. And you got to remember that these are really, this circuit has nothing but a voltage and a diode. Okay. And so, if it's simple or complex or whatever, it's not that big of a deal. But a real circuit, again, might have, 4 diodes, 20 transistors, and, 15 resistors would be probably like a small circuit. And life would get pretty hard without some simplifying assumptions in those cases. So I'm going to keep that in mind and sort of try to extrapolate in your head how the benefits of having a simple model and how intractable those problems be if you're still dealing with exponentials and natural logs when you have a bunch of diodes, a bunch of transistors, and so on. Okay, but say just for this case, let's look at the other models, okay, that we used and whether we can use them or not in this case. Okay, so let's say that you are going to use, well, for this particular case, okay, the constant voltage, sorry, the ideal model and the constant voltage model are completely useless. Those are really simplifying models. So this was the ideal model. So this is ideal. And boy, that was a bad job of this one. Ideal model. And this is the constant voltage model. So the ideal model, you know, just the model the diode as this. The constant voltage model the diode as this. And so for solving this type of problem, both of those models are pretty much useless because, you know, it's a real binary system. Either the diode is off or the diode is on. There is no concept of the diode being on a little bit and turning it on a little bit more in this idea. It's either on, okay, which you get this infinite or zero resistance, or it's off, in which case you get infinite resistance. And same with the constant voltage models. Okay, so there, in both of these cases, the diode, these models are only good if you're trying to figure out a general operation of your circuit. If you're really asking a question like this example is asking, example 3.18, about the diode being on a little bit and then changing that point, then these models are not going to help you. Okay, so basically what you're stuck with is going back to your, just using your exponential model. Okay, which V sub D, I sub D, and this had this equation ID is I sub S exponential of VD over VT, and this was only out here. Okay, or you can looking at another way, and I'm just these are the same equations, I'm just writing it in terms of voltage versus current. So VD is VT exponential of ID over IS. Okay, so basically that's what you're left with. So let's try to use that to solve the same thing, same problem. Okay, so again, the problem is you are biased around a milliamp. Okay, so this is a V bias, we don't know what it is. And then what would a delta V of 1 millivolt do here? How would it change the current? Okay. So this is, let's say you were being hard-headed, you just, didn't want to learn how to use the small signal model. And, I'm just going to use, just this one equation is good enough for me. So let's try to solve the same problem. Again, this guy, which was, again, fairly simple without doing that. Okay, so the first thing I do is the first step, I need to find V sub D at 1 milliamp. Okay, so the equation for that is VD is VT natural log of ID over IS. Well, the example didn't even give us I sub S, so now we have to come up with something for I sub S. But let's assume that we're given that. So let's say we just assume I sub S is 10 to the minus 15 amp. It could be anything else, but I'm just going to use that as an example. Okay, so V sub D in that case is 26 millivolts, natural log of 1 milliamp over 1 times 10 to the minus 15 amps. Okay, so now you pull out your calculator. I guess I'll do that real time. I got, just to kind of prove to you guys that it's, well, you guys know, but it takes a little bit of time because it's sure you're not going to do it in your head. So it's one. I take the natural log, which is This gives me 27, and this is 26 millivolts. Multiply that by, and I get 7.7184 volts. Okay, with some other numbers here. It's approximate. Okay, so I got, this is the voltage V sub D at which I'm at 1 milliamp. Now the question for the example is, now what happens when V sub D changes by 1 millivolt? So now, so if I was going to say this is VD1, I got to say VD2 is VD1 plus 1 millivolt. Okay, so it's 0.7184 millivolts plus 1 millivolts is 0.7194 millivolts. Okay, and now to get the current at that new point, I get ID2 is I sub S exponential of 0.7194 millivolts over 26 millivolts. And when you calculate that, you end up with 1.0392 milliamps, or your delta I was 39.2 microamps. Okay, calculating it the sort of the full way. Okay, so from the small signal, so we calculated the same thing here, and we calculated 38.4 microamps from the small signal form. So 38.4 microamps is delta I. Okay, which is certainly very close to the number we just calculated. It's, you know, off by less than a microamp. Is that right? Yeah, by 0.8 microamps. Okay. Now notice, you know, I had a natural log calculation here. I needed some bit of information that I didn't even need in that other approach to solve. I then had to, you know, carry a bunch of decimal places. If you cut this short and plugged in the 1 millivolt, you wouldn't really get the right value. And then I had to do an exponential calculation and multiplying it again by a 1 times 10 to the 15, 1 times 10 to the minus 15 number. Anyway, long story short, a much more detailed calculation. It's going to take you a while longer to do it. I did a natural log and exponential, neither one of which would you be able to do in your head. Okay, so you'd have to calculate each one. And again, just think about, this is a single diode we're looking at. Imagine multiplying the complexity of using the full model versus the small signal model if you have a large circuit. It's a huge difference in complexity. Okay, so once you get that, and you know, of course, the other part of the discipline is figuring out when you can use the small signal model and when you can't. Again, it depends on the size of your input signal. But once you figure that, it's a very powerful tool. Okay, so that's the small signal model. We're going to leave it at that. Hopefully, we're going to get some practice in the homework examples. So now we're going to move on. Hopefully, finish everything I want to finish in chapter 3 today. So just a reminder that our quiz number 2 coming up next Tuesday will only cover up to the point of small signal model. So it will not be covering what I'm going to talk about today. Okay. So basically, if you're just focusing on studying for the quiz, basically we'll be covering the different diode models and not the analysis of the half wave and the full wave rectifier. Okay. Having said that, let's talk about the half wave rectifier. So I think we've looked at this circuit. We looked at the circuit a couple of times, and that what it does is if you have a Vin that's sinusoidal with time, what this diode does is it turns on. So this diode, when Vn is on a high cycle, the diode becomes a closed closed switch, and when the input is on a negative going cycle, so this is Vn versus time, the diode turns into an open circuit. Okay, so basically what does that do? If I have a closed circuit when Vn is driving this thing, the output is just going to follow Vn. But because remember, this is the constant voltage model of the diode, I have this extra battery in the path. So the output is going to look like Vn minus a Vd on, okay? And then when Vn gets to zero, or sorry, when Vn gets to Vd on, the diode turns off, and then we have to use this model of the circuit, okay? So basically what you end up on the V output is a curve that looks like that. So you're letting go the positive half of the curve on the output. And whereas Vn has no DC component, this actually has a DC component. If you average the signal over the full period, you only have stuff in the positive and nothing in the negative to get rid of this DC value. So the DC value of this is going to be some sort of RMS value around that. Okay, so that's our half wave rectifier. And just by the way, if you flip the direction of the diode, so the cathode is pointing this way, then you're letting the negative part of your Vn go through, okay, and blocking the positive side. Okay, so now though, remember that, you know, what we're using this for most likely is for something like a regulator. So we have the 110 volt outlet from our wall plug is, you know, 110 volt AC at 60 hertz. That's what we have. And you want to charge your cell phone. So a cell phone wants, I don't know, wants something like that. With time, it doesn't want any change, and it wants it to be, I don't know, 3.4 volts or 2.4 volts or whatever it is. Okay, so we want it to be constant. So somehow we got to figure out, instead of, so this is a good start, but we got to figure out, instead of this, we want to get a constant voltage with time. So how do we do that? Well, you can do that by sticking a capacitor in front of your diode. And what does that do? Well, so on the positive going wave of your input, the diode, let's, for the sake of discussion, let's say the capacitor starts with, so the initial condition, initial charge on capacitor, let's say it's 0. Okay, so the voltage, let's say we start, the capacitor starts with 0 volts here. Okay, so it starts with 0 and means that as soon as the Vn gets larger than a Vd on, okay, starting here, that guy's going to turn on, the diode is going to turn on, and the capacitor is going to go up to this value, to the where the Vn peaks. Okay. Now, as soon as Vn starts going down, what happens? This point, so that we're going up and now we're coming down. So as soon as you start coming down, this point dips below this point. So the anode dips below the cathode as soon as the input starts going the other way, starts getting smaller. And as soon as that happens, the die is going to turn off. Okay, so as soon as this point happens, the diode is going to turn off. And because it's a capacitor here, it's going to keep that voltage, because for the capacitor to change its value, the charge needs to go somewhere. And if this diode is off, the charge can't go anywhere. So the charge is just, so remember the voltage Q is equal to CV. So the voltage on a capacitor is Q, the charge on the capacitor over the capacitance. So the capacitance doesn't change. Okay, the capacitance is whatever the capacitance is. The charge has nowhere to escape to in this direction. And so the voltage then stays constant. So basically you got this output voltage. Now, as this thing is off during this whole period, that guy is off, that guy stays constant. Okay, goes here, still stays constant. You don't really ever turn on the diode again, because this point always ends up being either at V out or right or below V out. Okay, after you get V out, this peak V out stuck here. So after V out reaches V peak, which is this guy, minus VD on. After that point, which is right here, after that point, this input goes to V peak, or goes to negative V peak, comes out to what, positive V peak. There's no reason for this diode to turn back on, because the input has to go all the way back up to VP minus VD on before it turns on. At any point below that, any of these points, the diode is off. Here you could think of it as turning on, but because there's zero voltage between this point and this point, you still don't have any charge flow across. So long story short, the output just stays constant. Okay, great. So now, it looks like we got our circuit. We can just plug this V out. So plug the V out, the output of the circuit, into our, so if you just had this, we stick this onto our cell phone, because we have this constant, we have this constant voltage that we want it. I mean, assuming that we've got, this is at 3.4. Okay, so it seems like we're done, but not quite. Okay, because what happens is that, I'm going to come back to this slide a little bit later, but anyway, what happens is the cell phone itself starts discharging the capacitor. So remember I said that here there is no place for the charge to go to once this diode closes. But if I have a cell phone connected here, okay, sorry, let me I'm redrawing the same darn thing over and over again. I can model that cell phone draws current from this capacitor. As it's charging, it's pulling current from the capacitor, pulling charge from the capacitor. So I can model that cell phone as a resistor, that it's starting to get this pull charge. Okay, so charge is going from the capacitor to my cell phone. Okay, and that has the effect of draining this capacitance. So instead of this thing staying flat, what it does is it starts discharging into my load. This starts, as it's charging the cell phone, the capacitor is getting discharged. So the waveform starts going down, And now, because this thing is dipping down, when Vn comes to whatever this point was, whenever it points, remember the cycle is 60 hertz. This is the output wall plug. So it's 60 hertz or 16 milliseconds. Okay. Depending on how much you dipped during that time, at some point, your Vn is going to be, this Vn at some point is going to end up being a VDON higher than your discharging capacitor, and this diode's going to turn on and start charging up the capacitor again. So you're going to get this kind of, instead of getting a straight line, sort of getting a straight line like you wanted, because of the cell phone itself or because of your load with cell phone, computer, whatever it is, it's going to have this bumpy voltage, okay? And the frequency of this bump, of the separations, is whatever's the frequency of your input line. In the US, it's 60 hertz. Different countries, some places are 50 hertz, whatever, or depends on your input. Okay, so you get this ripply output coming out. So, and this thing is like not a good thing, okay? Because again, your cell phone battery, etc., is their ideal situation is a flat line. If you take a VLSI class later on in your careers, it's like a senior level class, whatever, or other classes looking at digital circuits. This basically, when your voltage supply is not constant, this basically messes up with your circuit. It adds noise to your circuit. It basically creates a possibility where your circuit basically does something incorrectly. Okay, so the ripple is bad, but it's a function of the circuit we've created. Okay, and it just depends on the value of capacitance and the value of the load. Okay, assuming that this frequency stays the same. So if you're using the wall voltage, it will stays the same. It's at 60 hertz. And then your load is what the load is, right? It's your cell phone, so you don't have a choice. Your only choice is to pick different values of C1. So if your C1 is large, again, remember that Q is equal to CV. So V is Q over C. Let's say your cell phone draws a certain delta Q over time, is pulling in the charge at a certain rate. The larger this capacitor is, the less of a drop the less of a difference you'll get. So the smaller this capacitor gets, this drop gets smaller and more. Sorry, the drop gets more and more. Okay, which is a worse and worse situation. And if you had a very small capacitor, in between, you just completely discharge to ground and then turn back on again when Vn gets to be VD on, etc., which would be a disaster. And so, I guess the disaster really depends on how sensitive your circuit is, but usually you do not want this ripple. So for digital circuits, ripple of more, depends on the digital circuit, but more than plus minus 5% or plus minus 10% is catastrophic, basically, which means your circuit may not work. So if you use a microprocessor or something like that, and your ripple is plus minus 20%, your circuit may not work properly. Okay. So, and by the way, I want you guys to notice one thing. It's a minor point, but some of you may have that question. So the real the ripple, the way this thing discharges in this model isn't a line. It's an exponential, because remember, this is a RC circuit discharging. And if you remember from your RC, from your previous circuit classes, this will be an exponential drop, which looks like that, not like a line. But if you just look at a small portion of this, it looks like a line. So that's why these things kind of look like a line. But these are also, exponentials if you wait long enough. So, but if your period is short, it looks like you're dropping by a small amount. Okay, so this is the bottom line here. This equation basically comes up with what happens. So notice that, as you know, this is solving for this V output as this guy is discharging. So this RC is discharging, RLCL. So this is the starting point. Then you get an exponential discharge having to do with the RL and C. Okay, and if this is small enough, we can do this Taylor series expansion, which is something Taylor series. This is just for your interest, guys. You don't need to do Taylor series expansions in this class anyway. So a Taylor series expansion, if you have something like exponential of x, you can, and you can basically, that's equal to 1 over x over 2 plus x squared over 4 plus x, at dot, 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 dot. You have to go to infinity, of course. Now, if x, or this number, if that's small enough, then you can basically just forget about these following terms. Okay, I'm sorry, guys. This should be x, and this should be x over 2, etc. Okay, so basically that's what going from here to here is. We're getting a Taylor series expansion of this guy, which is just, getting 1. This had a minus in it, so it ends up being 1 minus t over, this was the x. Okay, and then it goes and multiplies it out. The upshot is this. The upshot is this equation, which is really the only one you have to think about after lots of approximations. Okay, and basically what it says is that this is the voltage you start with. It says the ripple voltage. So this is just this ripple. Okay, so this change, okay, is your starting voltage divided by the load, the capacitance, and the frequency, operating frequency. So you want this ripple voltage small, okay? So what can you do? As I said before, if you're stuck with a certain input frequency and a certain load resistance, so if your cell phone pulls whatever current it pulls, and the wall is always pumping out at 60 hertz, you're basically limited to picking a large enough capacitance that you can get the ripple to a reasonable number. Okay, and as usual, the problem is that large capacitances, it's an engineering problem, because as capacitors get larger, they get bigger physically. You go from something that's maybe 1 by a couple of millimeters to something that they could get as big as big capacitors, or could be a centimeter on a side or bigger. And sort of the sizes step up. And as your capacitors get bigger, they tend to actually have their own inductance and resistance. They tend to ring and have all sorts of problems. So big capacitors are something you want to avoid from a size point of view. They get expensive, and again, they have like some weird ringing issues having to do with the fact that they have their own internal inductance, which gets big and so on. So it looked like a kind of a oscillating tank circuit. Okay, but anyway, that's the upshot. That's really kind of the bottom line with this half-wave rectifier, which is that you want to size, this is the equation for the ripple. We want to minimize this ripple. Okay, so I'll write that down. Minimize this thing. And to do that, typically what you end up having to do is to increase your capacitance. Okay. And I'm not going to talk about the maximum direct current for a second. So let me just go back and talk about this, what was on this slide. So this is a unpleasant artifact of this half-wave rectifier. So we talked that what happens at the output stays flat, right? Because this capacitor holds it. Again, for the second, don't think of the ripple, which is sitting on top of this. It won't change what I'm about to say. But let's say the output stays flat. The input, it's still chugging along, going to the full negative value. So if you look at the voltage across this diode, it tends to go to twice the peak voltage. So if this is going from VP to minus VP, the voltage across this diode goes to 2 VP. Okay, so why is that important? Well, if you have a real diode, and you at some point, if you put a very high reverse bias voltage across it, at some point it's going to break down. Okay, at some point it's not going to work anymore. So what it's going to look like is there's some description of this in your book. I didn't really get into it, but we have this curve, and this is reverse bias. We assumed this just goes forever, but in reality, if you put enough voltage, if you go far enough out, this tends to break down again here, and this is the breakdown voltage. And depending on how bad that is, your diode can recover or not, but notice how it's kind of like sort of turning on again. And again, this is I don't know, depends on the diode. It might be minus 10 volts, might be minus 20 volts, whatever diode is. The upshot is when you build this circuit, you have to be careful to buy or get a diode that has a high enough breakdown voltage. Okay, depending on your input swing, it has to have a high enough breakdown voltage so that it does not reach this point. Okay, because it will see twice the input voltage. So that's what you have to remember. Okay, so that was the half-wave rectifier, which was cool. But I think Loy asked this several lectures ago. It seems kind of wasteful that our input has these 2 cycles and we're just using half the cycles. We want to use these cycles too. Okay, how do we do that? Okay, well, there is a way, and it's called the full wave rectifier. And so if you use this circuit, you would do something in our input would have plus and minuses, and you would flip both sides over and be able to use, sort of the entire energy of your input. Okay, so how do we build that? Well, I think it's easier if how do we do this? I think it's easier if I draw this for you guys. I mean, I'm sort of like drawing the same thing that's in the lecture notes, but I'm just gonna sort of step through it in some ways. Okay, so this is called a full wave rectifier. And the schematic looks like, I always have to look here, draw this thing. And it's also called a bridge rectifier. I have no idea why it's called a bridge rectifier. Okay, you guys already see we're sort of getting to a larger number of diodes. And you can see like things could get complicated if we were going to start looking at the exponential models here. But fortunately, we're not. And then I'm going to draw this the load resistor as this. Okay. So now before I describe the circuit to you guys. One very key point. So a key point is that up till now, okay, our outputs have always shared a reference with the input. What do I mean by that? Okay. I mean, like if you look at a circuit like our half-wave rectifier, if I look at this, this is V out, V in, diode. Okay, and all the other circuits were kind of like this in some ways. Notice, okay, so here's our VN, this is our V out, but VN, because it's a voltage, it needs to refer to something, right? It's a voltage with respect to something else. VN is referred to ground, okay? And in fact, V out shares the same ground with VN. So they're both referring to the same node on the circuit. So notice this is not the case here, okay? Notice this Vn is defined as the voltage drop difference between these 2 points, okay? And V out is defined as the voltage reference between these 2 points or across the resistor. And so this reference point is not the same voltage. It's not the same node, okay? Whereas in all the other circuits we've looked at was the same node. And the reason I mention this is because it's kind of the secret to the magic of how this thing works. Okay, so anyway, that's like a key thing. Okay, so now let's take a look. And to look at the operation, it helps to draw this in a slightly different way. So I'm going to redraw this. It's not something that I've come up with. It's just how, if you'll see in the book, it's redrawn the same way. It's a little bit easier to try to understand how it works. And the way you draw it is I kind of draw 2 of the diodes facing, whoops, I always get this thing hosed up. Okay, 2 of the diodes facing this way. And so this is the same. I'm going to use the same numbers as the other one, D2, D1. I'm going to draw the other diodes in red. Oops, that's a real. I'm going to draw the resistor in green. Okay, so this hopefully is the same as this guy, as just drawn differently here. And hopefully in a way that's like we can use it as a starting point to understand how this thing works. Okay, and then remember that Vn versus time is doing something like that. Okay, so let's see what happens. So first of all, in the positive cycles of Vn, so like basically we're just going to look at here, here, here. So in positive Vn half cycles, so this is where Vn looks like, well, let me draw this over here. So just start here. It's easier. So in positive Vn half cycles. So Vn is kind of doing that in those half cycles. What happens is Vn, when Vn is positive compared to the plus node is positive compared to this negative node, what happens? So basically this guy turns off, this guy turns on, this guy turns on, and this guy turns on. Okay. And these two are off just because this point is more positive than this point. This point is more positive than this point. These two diodes, this diode and this diode, okay, end up being forward biased in that condition. And these two diodes end up being reverse biased. So those don't work. So the way it looks is the circuit ends up looking like this. So this D2 turns off. D3 turns on. I'm just using the ideal model here just so not to confuse you guys. And this is minus plus V out. And then D4 also turns on. This is just for the positive Vn half cycles. And so this is D4 and D1 is off. Okay, so that's Vn. Now, remember that V out is defined just across this resistor. So again, if I look at it, if I stretch out the circuit, it's going to look like this. And if I draw it one more way, is just if I just straighten it out, it looks like D4. Okay, so for this positive half cycles, V out is just equal to Vn for positive half cycle. So for these ones also, V out is going to look like that. Okay. All right, so that's for this positive. Now, if you look at V in negative half cycles, so if we look at Vn, so it's when Vn is going negative. Okay, for those, the other two diodes turn on. Okay, so if I was going to redraw this thing, now D2 turns on, D3 turns off, D4 turns off, and D1 turns on. Okay, so now this path is on. Okay, if I redraw this guy, notice a difference here. If I just redraw it, maybe I'll try to squeeze it in here. If I redraw this guy, it looks like this switch. But notice here, because now we're going like this, V out is changed its polarity with respect to Vn. So if I'm looking at V out, I got to look at V out like that. So here, V out is equal to negative Vn on the negative half cycles. Or because Vn is doing these negative bumps, V out is gonna do positive bumps. So if I add these things together, I end up getting what I want, which is that Vn is doing this, and V out. So this is Vn for this time. This is V out for this time. I want to get these positive half cycles. Okay, so going back to the first thing I said about this, now hopefully maybe it'll take you guys a couple of times around to think through this. The fact that V out does not share the same reference as Vn means that we're basically flipping this guy around. These, you can think of these as being switches that basically flip the relationship between V out and Vn depending on which direction Vn is going, to always assure that V out is outputting a positive version of Vn. Okay, even when Vn is going negative, this guy, because of the different set of diodes, turn on. So we either turn these guys on, to make this thing have a positive relationship with Vn, or negative half cycle, these switches magically these guys turn off and they turn on to give you a negative relationship between Vn and V out. So that way you always end up with a positive V out. Okay. So we might have to go through that a couple of times, but anyway, this is probably one of the more complex circuits to get your head around. But the advantage is, you're not going to run into having to figure out this circuit very much in real life or in the quizzes or homeworks or anything. What you really have to remember is that it's a full wave rectifier, and that it basically allows us to use both positive and negative half cycles, and that I think I'm just going to jump, Where's the equation for this thing? But I didn't bother to put in the equation today. Well, I guess we have the same really equation as this guy. Okay, Vp minus Vd on RO. So you end up with approximately the same equation. It's a little bit different. Let me actually write it on over. Well, I'll not write it here. Hopefully I won't get this wrong. Okay, so the half wave rectifier, we had sort of, these ripples because we only were using half cycles of Vn. Okay, so we had these ripples like that. But in a full wave rectifier, we end up using twice as many cycles of Vn. So if I was going to redraw it like this, it would sort of look like I would get another pulse here, another pulse here, because I am basically following both plus and minus versions of Vn. So basically what happens, if you remember, so again, the equation for the ripple was V peak minus VD on over R load C1 F1. Here for the full wave rectifier, we have two diodes in our path, so it's slightly, from that point of view, it's slightly worse. But what happens is, because it looks like our frequency now, this frequency is half this frequency. So the other way to look at it is this is twice the frequency of this guy. So I can basically end up with a factor of 2 here, given the same circuit, which means that essentially I've cut my ripple in half going with a full wave rectifier than with a half wave rectifier. So, and in practice, because of that, you essentially all the time, if you're buying a rectifier, building a rectifier, or, have something with a rectifier in it, it's almost always, ends up being a full wave rectifier. Okay, guys, think I'm running out of juice. I'm gonna stop it right there. That's really all I want to cover in chapter 3. This was the diode circuits. And again, for the quiz, you only need to worry about small signal models and anything before that. You don't need to worry about most of what we talked about in terms of rectifiers, etc., in the class today. And then after the quiz, then we're going to start with chapter 4, which is bipolar transistors. Okay, good luck, guys. Take care.